Hi there, this is Capacitance lesson 1. We're going to look at Q equals Vc. So what are capacitors? Capacitor is a device for storing electrical charge. Most capacitors consist of two parallel conductors or plates separated by a thin insulator. The insulator will be air in the simplest case. There can be other insulators. We'll look at that in a few lessons' time. So some uses of capacitors include voltage regulation in power supplies, timing circuits, tuning circuits, and in backup power supplies. The capacitor symbol is in the bottom right. Remember to pause at any time if you need to take some notes. So how does a capacitor charge? So when a voltage is connected to the capacitor is in the top of this diagram, and this. Extra electrons flow onto the right hand side plate, so they come from that's the positive side of the battery, or the cell, that's the negative side. So the electrons come from this side and flow in this direction. So the electrons flow onto the right hand side plate. This produces a relatively large electrostatic repulsion on the electrons on this side. And what it does, it leaves the positive protons behind. So essentially the electrons come around here, deposit themselves on this right hand side plate, force the electrons from the left hand side plate via electrostatic repulsion, and then they flow this way, and then we're left with negatives on the right hand side and positives on the right hand side. Sorry, the left hand side. The rate of flow of charge, the electric current, falls exponentially against time from an initial value, I0, as the capacitor becomes fully charged. And it's because it becomes more and more difficult to remove electrons from the positive plate, and there's also less room on the right hand side for electrons to be deposited. So an analogy that I could think of would be filling an empty cinema. So if you had an empty cinema and had maybe 200 people and just said, right, sit down, people could sit down wherever they wanted. The rate of flow of people going into the cinema would be high to start with. And when the number of seats started to diminish, the rate of flow of people would fall. And it's the same with filling an empty bus. So you can get on a bus, if there's lots of seats, it's really easy to get on the bus and sit down. When it starts to fill up, the rate of flow of people sitting down would decrease. And it's the same for current charging a capacitor plate. There's a graph on the right hand side. So let's move on. So what is capacitance? Capacitance of a capacitor is defined as the charge stored per unit potential difference change. So capacitance is charge over voltage. So the unit of capacitance is farads. It's also, because of the Q over V, coulombs per volt. So 1 coulomb per volt is 1 farad. So we've got Q equals CV or VC, and V equals Q over C. I like to remember Q equals VC. It's on the data sheet anyway, but it's an old shopping channel, QVC. So it's very simple to remember that way for me. So Q's charge measured in coulombs, V's voltage obviously measured in volts, and capacitance is measured in coulombs per volt or farads. Just a quick reminder. So let's say nanofarad means times 10 to the minus 9. Micro you should know, but micro would be times 10 to the minus 6. And then one that you might not be aware of is pico. And pico is times 10 to the minus 12. Let's move on and do a table. So to use the Q equals VC equation, pause the video and do these 6 questions. And then I'll take you through the answers. So the first one, we get 50 microfarads, 200 microcoulombs, 12 volts, 25 volts, 50 microfarads, and the last one, we've got the pico at the right hand side, which is to power minus 12, is 900 picocoulombs. Okay, let's move on. Got some nice questions. So here's the first one, if you want to pause and have a go. A capacitor of 500 microfarads is charged by a power supply 4 volts through a 200 ohm resistor. Calculate A, the initial charging current, and B, the final charge stored on the capacitor. So the current would simply be I equals V over R. So the voltage is 4 divided by resistance of 200, which gives a current of 0.02 amps. Then to get the final charge, we need to do Q equals VC. So the voltage is 4 volts multiplied by the capacitance 500 microfarads times 10 to the minus 6. So that gives us 2 times 10 to the minus 3 coulombs, or 2 millicoulombs. Pretty straightforward. Let's move on to the next one. So pause and have a go. A capacitor stores a charge when charged to a potential difference of 5 volts. What will be the PD across the plates if the charge stored increases by 50%? So we've got Q equals VC. Well, Q equals CV, whichever. So if we increase the charge by 50%, then the voltage would also increase by 50%, because capacitance is a constant. So we've got the charge is directly proportional to the voltage. So if we increase by 50%, we've got 1.5 times the original charge. We would also have to have 1.5 times the original voltage. So we simply need to do the 5 volts multiplied by 1.5, which gives us 7.5 volts. Hopefully that went okay. Let's move on to the next one. So pause and have a go. An uncharged 5 picofarad capacitor is connected to a 1.5 volt supply and becomes fully charged. How many electrons are transferred to the negative plate of the capacitor during the charging process? So we need to calculate the full charge. So that's Q equals VC. So we've got the voltage, 1.5 volts, multiplied by the capacitance, which is 5 picofarads, so 5 times 10 to the minus 12. And that gives us a charge of 7.5 times 10 to the minus 12 coulombs. Then to get the number of electrons, we simply need to divide it by the charge of an electron, so 1.6 times 10 to the minus 19 coulombs, which gives us, it's two significant figures, 4.7 times 10 to the power 7 electrons. Let's do one more, a bit trickier. Hopefully that one went okay. So the next one, let's pause and have a go. Initially, a capacitor stores 800 microcoulombs of charge. When it loses half of this charge, the potential difference across it decreases by 50 volts. Calculate the original potential difference, and then secondly, the capacitance of the capacitor. So hopefully you had a go at this one. So the original starting point will be that the capacitance is the same in both instances with the original charge and when it loses half of the charge. So I can write the capacitance in scenario 1 essentially is the same as the capacitance in scenario 2. And we know that the equation for capacitance is charge over voltage, so I can say charge 1 over voltage 1 is equal to the second charge divided by second voltage. So charge 1, we know, is 800 microcoulombs divided by voltage 1, which is what we're going to figure out, equals the second charge, which is it loses half of its charge. So that becomes 400 microcoulombs divided by, and we know that the voltage decreases by 50. So we have the original voltage minus 50. So, therefore, I can say that V minus 50 over 50, sorry, over V1, is equal to 400 microcoulombs divided by 800 microcoulombs, so that's just a half. If you didn't get to this point and you want to finish this off, you can pause, and please do so. And there's a couple of ways of doing this. So we can multiply through by V, so we end up with V minus 50 equals 0.5V. Then we have V, take the 0.5V to the left hand side, so V minus half V is half V. Equals, and then the 50 on the right hand side. So V is simply 50 divided by half, and 50 divided by half is 100 volts. So that's the original potential difference. Well done if you got that right. So capacitance is simply charge over voltage. So we've got the charge, the 800 microcoulombs, so 800 times 10 to the minus 6, divided by the voltage. And the original voltage is 100. So the capacitance is simply 8 times 10 to the minus 6 farads, or 8 microfarads. Hopefully that's gone okay. Thanks for watching, I'll see you soon. Take care.